Another thing we can do with trigonometric identities, besides just using them to simplify trigonometric expressions, is to use trig identities to come up with even more trig identities. There's actually sort of a common cottage industry in finding new and interesting trigonometric identities. So here's an example. Let's prove that this equation is really an identity. So the idea here is if this equation is supposed to be true for every value of theta, or at least every value of theta where both sides are defined, there ought to be some way to take the left-hand side, do a big calculation, right? A big calculation step by step, and end up with the right-hand side. If we can do that, then we've demonstrated that the left-hand side is really equal to the right-hand side. So let's see if we can make it happen. So we have sine theta times cotangent theta plus tangent theta. One of the tricky things about identities is it's not always obvious what your next step should be, or even what side you should start with. So here I've started with the left-hand side instead of starting with the right-hand side. The reason I chose the left-hand side to start with is because it's more complicated. Usually it's easier to start with the more complicated side of your supposed identity and try to simplify it so that you end up with the right-hand side, rather than starting with the simpler side and trying to make it more complicated. That just seems kind of backwards. So let's start with this left-hand side and see what we can do. We'll simplify it and see if we can make it turn into secant theta. So let's see. Well, there are a couple things you could try. I guess one thing to try is just to distribute this sine theta. That seems like a sensible thing to do. So we get sine theta times cotangent theta plus tangent theta times sine theta. I reversed my order for some reason, but that's okay. Now what? Well, I guess what we could try next is write everything in terms of sines and cosines. Right here we have part of this in terms of sines already, so maybe we should make all of our tangents and cotangents also be in terms of sines and cosines. So that would give us sine theta times, let's see, cotangent is cosine theta over sine theta, plus tangent is sine theta over cosine theta, so that times sine theta. All right, and yeah, I see that some things happen here. So these sine thetas cancel, and we get cosine theta plus, and then in the second piece, we can combine the sines. We get sine squared theta over cosine theta. And then, let's see, well, to add these two pieces, I guess we could put these over a common denominator. So the common denominator for these two terms would be cosine. So let's make the denominator of this one cosine. But that means we have to multiply this numerator by cosine as well. So we get cosine squared theta over cosine theta plus sine squared theta over cosine theta. Then, well, look, now we can actually add these things since they have the same denominator. So we get cosine squared theta plus sine squared theta all over cosine theta. But look, I mean, anytime you see trig functions that are squared, you should wonder if you can use a Pythagorean identity. And yes, cosine squared plus sine squared theta, that's 1. So 1 over cosine theta. But 1 over cosine theta, that's secant theta. So if we look way back up at where we started with the left-hand side of this identity, and we ended up with just secant theta, which is the right-hand side of this identity. So this proves that this identity is a genuine identity. It really is an identity. All right, so the tricks that we used here was we multiplied everything out. we made a common denominator. And we used a Pythagorean identity. Those are the tricks that we used here. All right, let's look at another example of establishing an identity. So here's a supposed identity. Let's see if we can figure out if this is a genuine identity or not. We'll start with one side and try to turn it into the other side. So again, it's usually easier to start with the more complicated side. So let's start with 1 minus sine squared theta over 1 minus cosine theta. Okay. So for this one, I mean, I don't know. This thing on the right is a fraction. So why don't we try to make this or put this over a common denominator. 1 minus cosine theta. So we get 1 minus cosine theta over 1 minus cosine theta minus sine squared theta over 1 minus cosine theta. Now we can actually do this subtraction. So 1 minus cosine theta minus sine squared theta all over 1 minus cosine theta. All right. Kind of hard to know where to go from here, but you know, we have a squared on our sine function, so why don't we try to turn this into cosine, I guess. 1 minus cosine theta minus, so the Pythagorean identity for sines and cosines looks like cosine squared theta plus sine squared theta equals 1. And we can rearrange that to see what it says about sine squared theta. So sine squared theta is 1 minus cosine squared theta. So we can replace this part in here with 1 minus cosine squared theta all over 1 minus cosine theta. All right. Then, I don't know, seems like maybe we should distribute this minus sign because it seems like that's going to let us combine some terms. So 1 minus cosine theta minus 1 plus cosine squared theta all over 1 minus cosine theta. And now I see that, yes, we can combine some terms. These ones are gone. So we're left with minus cosine theta plus cosine squared theta all over 1 minus cosine theta. Now in this numerator, both terms have a greatest common factor of cosine theta. And while we're at it, we might as well factor out a minus sign as well. So let's factor out minus cosine theta from our numerator. The denominator is going to stay the same. And when we factor out minus cosine theta from this numerator, we're left over with, let's see, 1 minus cosine theta. Oh, well, now these cancel. And we're just left with minus cosine theta. Seems like that's about as simplified as it's going to get. What were we supposed to get? Go back to the top. Oh, we were supposed to get minus cosine theta. So we're done. We've demonstrated that 1 minus sine squared theta over 1 minus cosine theta is equal to minus sine theta. All right. Here's another one we can try. Tangent cubed x plus tangent x equals secant squared x times tangent x. To me, it seems like this one on the left is more complicated. It's not a lot more complicated, but it's a little more complicated. So let's try it. So tangent cubed x plus tangent x. And I don't know, I mean, the only thing that comes to mind for me with this is there's a common factor here. Both of these have a factor of tangent, so we could factor out this tangent like this. So factor out tangent x, that leaves us with tangent squared x plus tangent x, sorry, plus 1. But tangent squared x plus 1, according to one of the Pythagorean identities, that's just secant x. So actually it looks like this identity, I'm sorry, this is secant squared. What am I thinking? So we're done. We turned the left-hand side into the right-hand side. So we've demonstrated that this identity really is true for every value of x. Well, every value of x where both sides are defined. All right, final example. Let's try to demonstrate this identity. So this one, it's really hard to know where to start on this one. And sort of my final trick that I have for identities is to think about where we want to end up. Think about our goal. Okay, so probably we want to start with sine theta cosine theta over cosine squared theta minus sine squared theta, just because this seems like the more complicated side. So this is what we're starting with, and our goal is to turn this into tangents. So, you know, to turn this into some tangents, we have to get some sines over cosines. That's how you make tangents. You divide sines by cosines. And there are two places where sines show up. Right? There's a sine here. So we need to get this sine here over a cosine. And there are two copies of sine right there. So we need to get that over some cosines as well. And so it seems like this numerator, we want it to have its own denominator. We want to have some denominator here. And this denominator, we want it to have its own denominator. We want some denominator here. And what we want in these denominators is cosines. Well, we can make that happen. Right? We can multiply this by 1 over anything we want over 1 over the same thing. Right? As long as we put the same thing in these two spots, we haven't changed what this expression is. We're only changing how it looks. So, you know, we want a cosine in the under this sign right here. So let's put a cosine here. But, you know, that's not good enough because the cosine that we've written here, it's just going to cancel the cosine that's already there. So we need another copy of cosine. So let's put a cosine squared down here. But if we put the cosine squared in the denominator of the numerator, we have to put a cosine squared in the denominator of the denominator. So down here. All right, let's see what this does for us. Right, so thinking about the goal prompted us to multiply by this whole mess here. All right, now first let's think about the numerator. So I'm going to take this and multiply it by that stuff. You get sine theta times cosine theta over cosine squared. Cosine squared is cosine theta times sine theta. So I'm going to write those cosines separately like this. Okay, you can kind of see why. It's because these, the cosines on the right, those are going to simplify away. And the remaining stuff over here, sine over cosine, that's going to give us a tangent, which is what we wanted. All we need to do is work out what happens to the 1 over cosine squared in the denominator. So we're going to have to distribute it here like that. So we get cosine squared theta that was there to begin with times 1 over cosine squared theta minus sine squared theta times the 1 over cosine squared theta that we're distributing. Okay, so we get this. Now this numerator piece right here, all that's left over is a sine theta over cosine theta. That's tangent theta. right? Now for our denominator, there's a lot of simplifying we need to do here. This cosine squared theta times 1 over cosine squared theta, that simplifies. We're just left with 1 minus, and here we have sine squared theta over cosine squared theta. But that's tangent squared theta. And that's what we wanted. So we're done. All right, so those are kind of the main tricks for dealing with identities. Think about using common denominators. Think about multiplying things out or factoring things. Keep an eye on your goal, and whenever you see something squared, think about using the Pythagorean identities.